Hello, everyone, and welcome to the HPC on AWS virtual event. My name is Barry Bolding. I'm the Director of High Performance Computing at AWS, and I want to welcome you to this two-day jam-packed event. We have talks and tutorials that we hope will be informative and exciting as each of you are progressing on your HPC journey in the cloud. This kind of virtual event is new for us. We all wish we could be gathering in person in Atlanta for SC20, but this year we know we have to do things differently. I want to thank Intel for their sponsorship of this event, and I want to thank all of the partners and customers who have contributed to the presentations that we have coming up. HPC is a community, and events like this can't happen without community. Over the course of 2020, AWS has continued to innovate for HPC across our entire product portfolio. Today and tomorrow, you will hear talks covering a wide range of services and solutions and partners, including tailor-made HPC infrastructure and networks, innovations and upgrades in our job orchestration and infrastructure deployment, and advances in high-performance storage and visualization for the cloud. AWS has a complete HPC portfolio today, and there's no workflow or application area that we can't handle. In addition, AWS has recently expanded the boundaries of HPC and launched our AWS Bracket quantum computing service. In today's keynote, you'll hear John Preskill, Amazon Scholar, discuss the future of quantum computing. At the heart of HPC on AWS is our innovative and tailor-made HPC compute instances. The AWS C5N is core to that set of instance types. Based on Intel Skylake processors, it's been the workhorse for tightly coupled MPI distributed machine learning workloads. In addition, we have a complete portfolio of CPU and GPU instances that fit everyone's computing needs. Later today, you'll hear some of the exciting work Xenotech has been doing for AWS in deployment of computational fluid dynamics applications and applications of a wide variety of performance instances. Innovative processor designs are critical in HPC agility. In one of tomorrow's talks, you can hear one of our machine learning solution architects, Fabio Nonata De Paula, talk about how AWS designed accelerators such as Inferentia are changing the way customers run their machine learning workloads. If you prefer an orchestration service with more of a feel of your on-premise cluster, Parallel Cluster is an ideal solution. Parallel Cluster integrates with all our major services and even gives you the ability to deploy your own software and schedulers such as Slurm in your parallel cluster system. These clusters can be temporary, or they can be, as some customers do, running continuously for several years. In 2020, we released support for multiple job queues per cluster, multiple instance types per queue, and support for new instances. We have CloudWatch logs for better budgeting and management, and support for new Linux versions. AWS has made major upgrades to our infrastructure deployment technologies in 2020, and there are several talks by AWS solution architects and partners like Ronan that will discuss the unique and powerful capabilities of Parallel Cluster. In 2019, AWS launched our Elastic Fabric Adapter. This allowed us to push our bandwidth and latency on AWS cloud infrastructure into the realm where both tightly coupled workloads like computational fluid dynamics using MPI could become production workloads on AWS. In addition, machine learning workloads such as distributed ML training can also be done utilizing the high bandwidth of the EFA network. I don't know how often I still hear the words, though, that AWS is not meant for MPI. This legacy on-premise thinking is not current with what AWS is capable of. AWS is dedicated to all HPC workloads, and with EFA, this idea that tightly coupled workloads are not capable of being run on AWS passes into the realm of mythology. Later today, you can hear Neil Ashton and Chetan Rao discussing running highly scalable workloads on EFA. You can't have HPC without high-performance storage. FSx for Lustre is a fully managed version of Lustre's parallel file system. And the Lustre file system provides throughput to hundreds of gigabytes per second and millions of IOPS. It provides consistent sub-millisecond latencies due to the parallel file system design, where clients can directly access both SSD-based storage and hard disk-based storage. It supports hundreds of thousands of cores for even the most massively scaled compute workloads. Tomorrow, Jordan Dolman will be discussing how AWS is breaking ground for new high I/O capable HPC algorithms. AWS Batch is one of our HPC flagship services, and it dynamically provisions compute resources based on volume and requirements of submitted jobs. It will plan, schedule, and execute your batch jobs across resources. There's no batch computing software to install. It allows you to focus on your applications and the results. Later today, Steve Kendricks, the product manager for Batch, will highlight the ease with which you field deploy and scale your modern HPC workloads. Evan Flodden, the CEO of Sakara, will be discussing ways that Nextflow takes advantage of AWS scalable deployments and scalability. We have so much to share over the next 2 days, and I have only mentioned a few of the highlights. We also have talks on how customers are using AWS Deep Computing Visualization, or DCV as we call it, to enhance their work from home scientific visualization. We have talks from SimScale on pushing the boundaries of aerodynamics in the cloud. We have talks from NVIDIA using Parabricks to push the boundaries of genomic sequencing in our fight against COVID. All of these talks are meant to show how capable, agile, and flexible the cloud can be for solving your critical HPC needs. I want to leave you with 3 words that I believe summarize the next few years and the challenges that HPC practitioners face. And hopefully over the next 2 days, you will find ways to rethink and reinvent the ways that you approach HPC. And through this process, you'll find ways to get to new and exciting results, whether you're in manufacturing, engineering, financial services, whatever area of HPC practicing you play. Hopefully we can help you and give you the tools to solve your most complex problems. I want to thank you for your time. I hope that you enjoy the upcoming seminars. The next up on the agenda is John Preskill, Amazon Scholar for Quantum Computing, who will be discussing innovations in quantum computing for HPC problems and what lies ahead in this exciting segment. Thank you.
Well, thank you very much. I'm honored to be here. I'm a theoretical physicist, and since last June, I've been an Amazon Scholar working at the Center for Quantum Computing that AWS has established on the Caltech campus. And for about 25 years, my main research area has been quantum information science. Quantum information is a broad field. It encompasses using quantum strategies to improve measurements, communicating with quantum states to protect our privacy, distributing quantum states over long distances, and using quantum simulators and quantum computers to explore the properties of exotic states of matter and to solve hard problems. I'm going to be focusing here on quantum computing, which is the application area which has drawn substantial interest and excitement and investment over the last few years, including at AWS. And as a physicist, the way I look at quantum information science is I feel we're still in the early stages of exploring a new frontier of the physical sciences, what we could call the complexity frontier or entanglement frontier. We are now developing and perfecting the tools to create and precisely control very complex states of many particles, highly entangled quantum states, which are so complex that we can't simulate them with our most powerful existing supercomputers, or explain how they behave very well with existing theoretical tools. And that opens new opportunities for scientific discovery. Just as if we want to explore matter at shorter distances, we build a more powerful particle accelerator, or if we want to explore the early history of the universe at earlier times, we build more powerful telescopes and instruments. So if we want to probe more deeply into the entanglement frontier, we will build more powerful quantum computers. And our conviction that this frontier will be fruitful to explore rests on two main concepts: quantum complexity, which is our basis for thinking that quantum computing is powerful, and quantum error correction, our basis for believing that quantum computers can be scaled up to large systems that can solve hard problems. And underlying both of those ideas is the concept we call quantum entanglement. That's the word we use for the characteristic correlations among parts of a quantum system, which are very different from the correlations we normally encounter in everyday life. You can think about it this way. We can imagine a book which is 100 pages long. And if it's an ordinary book written in bits, every time you read another one of the 100 pages, you learn another 1% of the content of the book. And after you've read all the pages, one by one, you know everything that's in the book. But suppose instead that it's a quantum book written in qubits, the quantum analog of bits, where the pages are very highly entangled with one another. That means that when you look at the individual pages, you just see random gibberish, which reveals very little information that distinguishes one very highly entangled book from another. And that's because in the case of the quantum book, the information isn't encoded on the individual pages. It's recorded almost entirely in the correlations among the pages. So if you want to read the book, you have to observe collectively many pages at once. That's the essence of quantum entanglement. And it's very different from any notion of correlation that we're normally familiar with. Now, if we want to write an entangled book, we don't use ordinary bits. We use what we call qubits. And a qubit is always realized physically in some way, and there are many different possibilities for building quantum hardware. A qubit could, for example, be carried by an elementary object like a single photon or a single electron or a single atom. And those are all quite remarkable encodings because although these are simple elementary objects, we've learned how to control them very accurately in recent engineering advances. Or a qubit could be encoded in a more complex system, like an electrical circuit conducting electricity without resistance at very low temperature. And that's also a remarkable encoding because it involves the collective motion of billions of electrons, and yet we've learned how to control it as though it were a single atom. And it's important that we continue to explore the possibilities for these alternative hardware platforms and others as well, because we just don't know at this stage which quantum technology has the best prospects for scaling up to large devices. Now, what's so interesting about these highly entangled systems is they're extremely hard to describe using ordinary classical information. So that if I wanted to describe all the correlations among a modest number of qubits, just a few hundred or so, I would have to write down more bits than the number of atoms in the visible universe. So it will never be possible to write that description down. Now, that in itself doesn't necessarily mean that quantum devices can do things that we care about, but we do have several reasons for thinking that quantum computers will be powerful. For one, we know of some examples of problems which we believe are hard for ordinary classical computers, but for which quantum computers, if we can successfully build them, would be able to solve the problems efficiently. The best known example is finding the prime factors of a large composite integer. And we think factoring is hard because really smart people have been trying for decades to come up with better factoring algorithms, and still The best algorithms that we have a runtime which grows super polynomially with the number of digits in the number to be factored. The theoretical computer scientists have given us arguments based on plausible assumptions that if we can carry out a modest size quantum computation and then measure all of the qubits, we are sampling from a probability distribution that we can't sample from accurately by any efficient classical means. But most tellingly, we just don't know how to simulate what a quantum computer does using an ordinary classical computer. And it's not for lack of trying. Physicists and chemists have been trying for decades to come up with better algorithms for simulating with computers the behavior of complex quantum systems with many particles. But still, the best algorithms that we have in hard instances have a runtime which grows exponentially with the size of the system, with the number of qubits. Now, we ought not to think that quantum computers have unlimited power, and in particular, we don't expect that a quantum computer would be able to efficiently find exact solutions to worst-case instances of hard optimization problems. But it's a remarkable thing that we think we've understood about the physical world, that there are problems which are too hard to solve with ordinary classical computers, which would be easy to solve with quantum computers. So it's a compelling question to understand what are these problems which are classically hard and quantumly easy. And we've learned a lot about that over the last 25 years. I think there's still a lot more to learn about that. But for a physicist, there's a natural place to look for such problems. And that is the problem of simulating with a computer the way quantum systems behave when they're highly complex and entangled. We expect that a quantum computer would be able to simulate efficiently any process that occurs in nature. And we don't think that's true of the computers we have now, which are not capable of efficiently simulating very highly entangled matter. So with a quantum computer, we should be able to go further in understanding the properties of complex molecules and exotic materials, and also explore fundamental physics in new ways. For example, by simulating high energy collisions of elementary particles, or the quantum behavior of a black hole, or the behavior of the early universe right after the Big Bang. Now, this idea that we can use a quantum computer to simulate highly entangled quantum matter is not new. It was discussed nearly 40 years ago by the physicist Richard Feynman, and only now are quantum computers getting to the stage where we think they're capable of doing interesting things. So evidently, it's hard to construct a quantum computer. And what makes it hard is that in a quantum computer, we want to simultaneously satisfy several criteria which are nearly incompatible. We want our qubits to interact strongly with one another so that we can efficiently process the information they encode. But we don't want the qubits to interact with the outside world, which would lead to errors in the computation. But we do want to be able to control the qubits from outside and ultimately measure them to read out a final result of the computation. And why is it so important that we keep the qubits isolated from the outside world? It's because of a fundamental difference between quantum information and ordinary classical information, namely that when information leaks out of a quantum system, that causes uncontrollable damage to the quantum state. That's the phenomenon we call decoherence. It's the formidable enemy of the quantum computer. And to overcome decoherence, we have to keep the information that's being processed in a quantum computer nearly perfectly isolated from the environment. And that sounds very difficult because our hardware isn't going to be perfect. But we've understood in principle how to use a noisy quantum device to do quantum computation reliably. And that is to make use of the idea we call quantum error correction. And the essence of the idea is that if we want to protect a quantum system from error, then we should encode the quantum information non-locally in a highly entangled state in a system with many parts. And then the environment might interact with those parts one by one. But in doing so, the environment doesn't acquire any information about what the encoded state is, just like that 100-page book I spoke of earlier, where you can't read the book by looking at the pages one at a time. And that means the quantum information is protected from damage. And furthermore, we've understood how, with noisy quantum hardware, to reliably and efficiently process quantum information that's encoded in this very non-local form. So where's the technology now? Arguably, we've recently reached a milestone, which has been called quantum computational supremacy. And the idea of quantum computational supremacy is that we think one of the most interesting things that we've ever been able to say about the difference between quantum systems and classical systems is that classical systems are not able to simulate quantum systems efficiently in general. And so there's a very strong incentive to validate that claim in the laboratory to the extent that we can do so. And the claim that quantum computational supremacy had been achieved was announced about a year ago by the quantum group at Google. What the Google group did is they constructed a quantum device called Sycamore, containing 53 working qubits laid out in a two-dimensional array, where neighboring qubits in the array could be acted on by entangling two qubit gates. And they performed a circuit of up to 20 layers of such entangling gates and measured the qubits at the end. Now, because their device is noisy, when they make that final measurement, they get a noisy answer most of the time. If they run this computation 500 times, 499 times, they just sample from noise. But once they get a valid result, and they can run the computation millions of times in just a few minutes and thereby extract some statistically useful result from the computation. But if I tried to simulate what the Sycamore device does with a classical computer, even the most powerful supercomputers that we have now, occupying 2 basketball courts and using megawatts of power, it would take much longer than it takes running on Sycamore, which is just a single chip device. It would take at least days and possibly much longer than that. So we can argue that the hardware is now working well enough that we can produce meaningful results in a regime where classical simulation is difficult. However, the particular task that was performed by Sycamore was not actually of any practical interest other than for the purpose of demonstrating quantum computational supremacy. It's useful to have a word for the era of information processing, which is now opening up. So I made up a word, NISQ. It means noisy intermediate scale quantum. Intermediate scale to indicate that we're talking about devices which have a sufficiently large number of qubits, more than 50 say, where we can't by brute force efficiently simulate what the quantum computer is doing with our most powerful existing supercomputers. But noisy reminds us that these devices are not error corrected, and the noise, the imperfect operation, limits their computational power. It limits the depth of a quantum circuit that we can execute reliably. Now, for physicists, NISQ is exciting. It means we now have the tools to explore the behavior of systems of many entangled quantum particles in a regime which has never been experimentally accessible before. And that may lead to useful scientific discoveries in the next few years. And it may also be that this technology will have practical applications of commercial interest, but we're not really sure about that. We shouldn't expect NISQ to change the world by itself, at least not right away. We should regard it as a step towards more powerful quantum technologies we expect to develop in the future. I do feel confident that quantum computing will have a transformative impact on human society at some point in the future, but we're not sure how long it's going to take to get there. There's kind of an emerging paradigm for how these near-term quantum devices might be used to solve problems. a kind of hybrid quantum classical scheme, it makes sense to use our classical supercomputers to the extent that we can, and then to boost their power with a quantum coprocessor. That might work this way. We can execute a modest size quantum computation and measure all the qubits, feed the outcomes of those measurements to a classical computer, which then returns instructions to slightly modify the quantum computation. And that cycle can be iterated until convergence, where the goal is to minimize some cost function for the purpose of finding an approximate solution to an optimization problem. Now, as I've said, we don't expect quantum computers to be able to efficiently find the exact solutions of hard optimization problems, but they might be able to find better approximate solutions than classical devices, or to find those approximate solutions faster. So should we expect that these near-term NISQ hybrid optimizers will be able to outperform our best classical computers running the best algorithms to solve problems of interest? Well, we don't really know. We're going to have to try it and see how well it works. But it's really a lot to ask, because the classical methods have been well honed over decades of development, and these NISQ processors are just becoming available for the first time now. Now, we don't necessarily have to be discouraged that we don't have convincing theoretical arguments that NISQ processors will have practical advantages. Now, we don't necessarily have to be discouraged that theorists aren't able to guarantee that these near-term quantum technologies will lead to important practical applications. We know of many examples in classical computing where algorithms turned out to have a significant practical impact, even though theorists weren't able to argue convincingly in advance that those algorithms would be powerful. We learned that through experimentation. A current example is deep learning. It's having a huge practical impact, yet theorists still have only a very limited understanding of why, for many applications of interest, deep learning networks can be efficiently trained. And at least in the near term, quantum computing may be a lot like that. There are various heuristic ideas for quantum algorithms that we'd like to try in these NISQ platforms without any guarantee that it'll turn out that the applications are useful and impactful. But as we experiment with the technology and with various possible applications, we'll learn more, and that may point us in the right direction for discovering new applications. But it will be a serious limitation in the near term that we'll have a limited number of qubits, maybe a few hundred, and because of the noise in the devices, we won't be able to run very deep circuits. So it will require a vibrant discussion among the application users, the hardware providers, and the algorithm experts to search for possible applications. And it will be important for the potential users to have access to a variety of quantum platforms to enable experimentation. And in fact, access to platforms will be provided by the AWS Bracket cloud service. Now, I've emphasized that about 50 qubits is a kind of milestone where a quantum device becomes too difficult to simulate with a classical computer, but actually we have devices with thousands of qubits, although the qubits are very noisy. In particular, the device provided by the company D-Wave Systems. The D-Wave machine, though, is not a circuit-based quantum computer like, for example, Google is developing. It's what we call a quantum annealer. It operates according to a different paradigm. It does solve optimization problems, and it's an impressive feat of engineering. But up to now, we haven't seen persuasive theoretical or experimental evidence that these quantum annealers are useful. It'll take further experimentation with quantum annealers to determine whether they can achieve a scaling advantage relative to the best classical hardware, running the best algorithms for solving the same problems. And in fact, the D-Wave system will be one of the platforms that will be accessible, already is accessible, through the AWS Bracket service. It's natural to wonder about the potential of quantum machine learning. It's possible that a quantum deep learning network can be trained with advantages over classical machine learning methods. We don't really know at this point for sure whether that's true. We're going to have to try it and see how well it works. The truth is, we don't currently have an example of a potentially practical end-to-end application of quantum machine learning with a significant advantage relative to classical methods, although such advantage may be found. It may be most natural to seek advantage in quantum machine learning for quantum problems, like trying to learn how to better control or characterize quantum systems. It makes sense that if we're trying through machine learning to learn a probability distribution, that a quantum advantage will arise if quantum entanglement underlies that distribution. Now, as I've emphasized, these NISQ-era devices will not be protected by quantum error correction, and noise will be a limitation on their power. We think the long-term solution to that difficulty is quantum error correction. It will allow us to scale quantum computing up further. But quantum error correction has a high cost in overhead, both in the number of qubits that we need and the number of gates we have to execute. Now, how high that cost is depends on the quality of our hardware and the application that we run. But as an example, let's suppose we want to use a quantum computer to break widely used public key crypto systems, and we have a hardware platform which has an error rate per gate of 1 in 1,000. That's better than was demonstrated by the Google device. And then we'd be able to run the algorithm on superconducting quantum hardware in a few hours and solve the problem, break the crypto system. But to have sufficient redundancy to protect the quantum information, we would need millions of physical qubits to reliably protect a few thousand logical qubits. So to reach scalability, to solve problems in that regime, we're going to have to cross a chasm from where we're likely to be in the next few years with hundreds of qubits to millions of physical qubits, and that's likely to take a while. It's important in the meantime to continue to advance the hardware, to achieve lower error rates, to have better methods for engineering the large systems, to define better algorithms and error correction protocols. All those things can bring us closer to the arrival of a truly fault-tolerant, scalable quantum computer. And these goals will be part of the core agenda at the AWS Center for Quantum Computing. So we're going to be facing the question in the next few years, what should we be doing with these intermediate scale quantum computers? And one important answer is that we should be using them to learn how to build bigger quantum computers. But we should be trying to do other things as well, exploring the possibilities for applications in the near term. If practical applications can be found that will help to ignite a virtuous cycle of progress where emerging applications will fuel further investment that will continue to advance the technology. If that doesn't happen, then it will require institutions and companies that are committed to long-term sustaining the field of quantum computing for the technology to continue to develop and realize its potential. Now, one thing that would make a big difference would be if we can come up with quantum hardware which is much less noisy than the hardware we have now. And there's an idea for doing so, which is more than 20 years old, that we could make quantum hardware much more reliable by developing suitable materials which have an intrinsic resistance to the noise that occurs in quantum devices. That's an idea that has been pursued aggressively by Microsoft for the last 15 years, but progress has been slow. Making materials advances is difficult. It requires a lot of investment and ideas and scientific advances. And so up to now, we haven't really seen a new material of the sort that we envision, which can make quantum gates much more reliable, though that could still happen in the future. And furthermore, we need more than just new materials. We also need better ideas about how to make the hardware substantially better. What will be the long-term impact of the development of the technology? Well, I don't think we really know. But for me as a physicist, it would be enough if the most important application of quantum computing turns out to be the one which we can most clearly foresee at present. That is, using quantum computers to advance our understanding of the behavior of complex quantum systems. The applications of that to chemistry alone will very likely, in the long run, lead to big advances in human health and the sustainability of our planet. But it's a very challenging thing to realize large-scale quantum computing. It's a grand challenge for 21st century technology, and it's going to take time. It's going to take sustained effort and new ideas, and we don't really know how long it's going to take to get where we'd like to go. So let me sum up. We've entered the NISQ era of quantum computing. Will these noisy intermediate scale quantum devices be capable of achieving an advantage compared to our best classical methods in running some applications? Well, we don't really know, but it's important to try to find out. By experimenting with the technology, we'll have a clearer idea of what the potential applications are. We shouldn't expect NISQ to change the world by itself. Really, the central goal for these near-term quantum platforms should be to pave the way for bigger payoffs in the future using more advanced devices. In the meantime, it's quite important to continue to improve the hardware to achieve, in particular, lower error rates in quantum gates. Doing so will extend the reach of quantum algorithms running on the near-term devices. It will allow us to execute larger circuits, and eventually it will lower the overhead costs of doing quantum error correction in the devices of the future. It's quite possible that the really transformative impact of quantum technology will need to be fault tolerant to incorporate quantum error correction, and that could still be a ways off, and we don't really know for sure how long it's going to take, but progress towards fault tolerant quantum computing should continue to be a high priority for the quantum technologists. And that type of long-term thinking is what's driving our agenda at the AWS Center for Quantum Computing. Well, thanks for listening to me.